So for this example, I'm going to walk you through the steps of using a z-score. And again, remember that a z-score measures the number of standard deviations away from the mean that a value lies. Well, here we're going to use a z-score to compare two different distributions. And here's why. So in this particular problem, if you read it, it talks about two applicants taking a test for a scholarship. And the problem with that is a scholarship committee has to decide which applicant is going to get the scholarship. Well, in order to do that, they're going to compare the test scores. But because the tests are totally different, it's a lot harder to compare those values. So remember this now. A z-score works on a standard normal, where on a standard normal curve, the mean for a standard normal is mu equals 0, and a standard deviation, sigma, is equal to 1. So if we label this standard normal with its mean and standard deviation, it looks like this: 0, 1, -1, 2, -2, -3, and a +3 out here. So it's 3 standard deviations to the right, 3 standard deviations to the left. This is what a standard normal does. Well, in the problem it says that Erica scored a 1080 on her SAT and Sam scored a 26 on her ACT. And they give you the mean and standard deviation for each one of these problems. So let's do Erica first. So for Erica, who scored a 1080, on her curve, it tells us that the SAT scores have a mean of 896 and a standard deviation of 174. So what we're going to do first is label this curve with this mean, which is 896. And now we're going to add and subtract the standard deviations to fill out the curve. Standard deviation is 174. So if I add, I'm going to only add these because we see that Erica scored a 1080. So it's going to be greater than the mean value. And so when I add 896 plus 174, I get 1070. We can see that Erica's score is going to be greater than that. So I need to go at least one more standard deviation. So if I add another 174, I get 1244 here. And we can stop there because we can see that Erica's score is going to fall somewhere close to this 1070 out here. So this is what she made on her SAT, right? Now, we need to do the exact same things for Sam's score. So it tells us that Sam scored a 26 on her ACT. So Sam scored a 26, and that ACT has a mean of 20.6. So what we're going to do is we're going to label Sam's curve with a mean of 20.6. So let's go ahead and label Sam's curve with that 20.6. And we're going to add that standard deviation because, again, she scored better than that. She made a 26. So we're just going to add that 5.2. So we'll get 25.8. And, again, she's better than that. So we need to go another standard deviation out. And so when we add that 5.2 again, we get 31. We can stop here. So basically, Sam scored about right here. And when I look at this and try to compare these based on the curves, I see that they're approximately in the same spots. So it's going to be really hard to do that. So how do I fix that? Well, I need to get them back down to the same curve. And in this case, I need to get them both back down to the standard normal curve. Because what the standard normal allows me to do now is it brings everything, it'll transfer both their means to a mean of 0 and both their standard deviations to a 1. And I do that by using the z-score formula. And the z-score formula is this: z is equal to x minus mu divided by sigma. So calculating both of these z-scores, if I calculate Erica's z-score, and I'll subscript it z of e for Erica, her score that she scored was a 1080. That's what the x represents. Minus the mean score of this curve is 896. We can see that from the curve drawn already. And the standard deviation for this curve is going to be 174. So when I calculate this, I get a z-score of 1.057, so I'll say 1.06. So we see that Erica scored a 1.06 standard deviations above the mean. That's what this means. When we're measuring this, we're actually measuring how far above the mean it is. Well, we know she did one full one away from the mean, and then she's 0.06 more standard deviations above the mean. And we're able to put that on this curve now, right here. So this is Erica's at 1.06. Now let's go calculate Sam's z-score. So this will be 26, because that's what she scored on her test, minus the mean, which is 20.6, divided by 5.2. So when I calculate that, I get 1.038. So we'll say it's about 1.04. So you can see that Sam's score approximately here at 1.04. And if you look at that, that's the number of standard deviations away from the mean. So we know she scored one full standard deviation away from the mean, but now she's 0.04 more above it. So now when I look at this, if I want to give it to the applicant who did better on their test relative to the mean, well, it looks like Erica did better on her test, not by a whole lot, but by a little bit more, because she is further away from the mean. So this is how we use z-scores to compare distributions. And this is why it's a measure of location or measure of position. It's where you're positioned at in the actual data set.